Hello and good day again everybody. Welcome again to Integral Calculus, and for today's video, we would be discussing about how we would be able to solve for plane areas using definite integrals. So in a given integration equation, so let's say that we have this certain equation right here. So the integral of a certain function x times dx with the limits of x1 up until x2. So this integral sign right here is actually an elongated letter S. So elongated letter S. And this elongated S right here signifies that we are actually getting the infinite summation of whatever differential function that we are trying to integrate. So in this example right here, we are actually getting the infinite summation of this function right here about these limits right here. And using that principle, we can now solve for the plane area about a certain graph. So let's say that we are to graph a certain function. So let's say that this is to be our Cartesian plane. So this is to be our y-axis and this is to be our x-axis. So this is to be our x-axis. And suppose that we are to plot a certain function. So let's say that that function is to be this one right here. So let's say that this is to be that certain function. And for pretend that we want to get the area of this graph about this point right here and this point right here. So if we are to use integral calculus in solving for this area right here, what we are actually doing is that we are getting the summation of all the differential areas about these points right here. So we would be getting this differential area right here, the differential area right here, differential area right here, up until you fill up this whole area right here. And that summation is to be your area. So if that is to be the case, so that can be rewritten as the infinite summation of our differential area. And using this one right here, of course, you must have your limits. And let's say that this one right here is to be our x1 and this is to be our x2. So this is now to be our x1 and x2. But how can we solve for this one right here? So your differential area is actually a chosen strip in your graph that you want to integrate. So let's say that this is to be our differential area. So I would just be making it a little bit bigger for you to see. So let's say that this is to be my chosen differential area. And let's say that this line right here has an equation of y is equal to function x. So that is for the equation of this particular curve right here. Okay, so if that is to be the case, this value right here is to be equal to y. And if that is to be y, this one right here is to be the value for your differential x, since this is to be your differential area. So from that, our new equation here, so this is now to be equal to the integral of, so what is to be our differential area? So our differential area is to be this area right here, and that is to be y times dx. So y times dx, and don't forget the limits x1 up until x2. So this is to be your formula for you to solve for this particular area right here. But if you can see, guys, you cannot actually integrate this directly, since this is to be y and this is to be dx. So the next thing that you would be doing is that you would be writing this value of y in terms of x. And if you can remember, y is equal to the function of x. So from that, this is now to be equal to the integral of fx times dx about your certain limit. So x1 up until x2. So for pretend that in this certain equation right here, you want to solve for the area from this point right here up until, let's say, x1. So you want to get this area right here. So your limits now would be from 0 up until x1. So from 0 up until x sub 1. So that is for your new limit. Okay, so let's have another graph here. So let's say that this is to be our y-axis and this is to be our x-axis. And let's say that we are to plot a certain function that is looking like this. So for pretend that this is to be our function, so let's say that this is to be y is equal to a certain function x. And let's say that we want to get the area bounded by this curve right here and the x and y axis. What we would be doing is that we would be assigning for a differential area, and we would be getting its summation about this point up until this point. I mean this point up until this point, I should say. So let's say that we are to assign this as our differential strip or our differential area. So if this is to be our differential area, so once again, the idea behind this is that we would be getting the summation of all the differential areas from this point up until this point. We would be filling all of this up until this point right here. Okay, so from that, since this is to be y is equal to fx, the height of this differential area right here is equal to y. And this one right here, for your differential area, this is now to be equal to d of x. So if this is now to be equal to, let's say, your x sub 1, and this is to be your x sub 2, for you to get the area of this, I mean, for the area bounded by the curve and your x and y axis, that is to be equal to, so your area is equal to the integral of the differential area. And from that, that is now to be equal to the integral of what is to be the differential area, that is to be y times d of x. So let's say that that is to be y times d of x. And what are your limits? So for pretend that you want to get the area from this point up until this point, so that is to be x1, x2. And take note once again, guys, that you cannot integrate this directly. You must rewrite this variable y right here in terms of x, since your dx is, well, in terms of x. Once again, you must rewrite this in terms of x. So from that, since your y is equal to f of x, so this is now to be equal to the integral of fx dx x1 and x2. So this is for your vertical strip. But what if that we want to have a differential area in an horizontal manner? Is it possible? So basically, it is. So if you want to solve for the area of this one right here, but you want to have a certain differential area that is horizontal, so let's say that this is to be your differential strip. So from that, this one right here is to be your x, and this one right here is to be your differential y. So from that, if you are to get the integral of our differential area, this is now to be equal to the integral of x times dy, since the area or the differential area is equal to x times dy, since this is just our very small rectangle. Okay, and what would be our limit? So if this is to be our y sub 1 and this is to be y sub 2, this is to be y sub 1 and y sub 2. But make sure, guys, to rewrite the value of x in terms of y, since you are to talk about d's of y. So it would be as simple as that. Okay, but what if we are to introduce another line here? So let's say that that line is to be this line right here. And what if the area that you want to solve for is to be this area right here? So let's say that you want to get this area right here. So how can we solve for it? So it is basically the area of this whole part right here minus this area right here, just for you to solve for this part right here, or you can integrate it this way. So you can once again assign for a differential area here. So let's say that this is to be our differential area or our dA. For pretend that this is to be our y2. So let's say y2 is equal to fx. So let's say that this is to be y1. So for the value of this part right here, or the height of this differential area right here, is actually equal to y1 minus y2. And as for its dx would still be the same, so dx. So from that, for us to get this area right here, that is to be equal to the integral of our differential area, and our differential area is once again this part right here times dx. And right now that is now to be equal to y sub 1 minus y sub 2 times d of x. And make sure to include your limits, so x1 up until x2. And once again guys, that if you are trying to integrate a certain function about dx, make sure to rewrite your function in terms of x, as we cannot integrate this directly. So there. For you to relate to our lesson better, let's have this illustrative example right here. So by integration, solve for the area bounded by the line y is equal to x plus 3 and the positive x-axis from the origin up until x is equal to 7. So the first thing that we would be doing here is to plot this line right here. And as you can see in this equation is actually linear. So when x is equal to 0, our y is now equal to, so 0 plus 3. So 0 plus 3, that is to be 3. And what if our x is equal to 1? Our y is then equal to 4. And what if our x is equal to 7? So when our x is equal to 7, so 7 plus 3, that is to be equal to 10. So from that, let's plot this. So let's pretend that our scaling here in the abscissa side is in terms of 1, or is an interval of 1. So 1, 2, 3, 4, 5, 6, and 7. And for our ordinate side, let's say that our scaling here is in terms of 2. So they would be having an interval of 2. So 2, 4, 6, 8, 10, 12. So there. Okay, so from that, when our x is equal to 0, y is equal to 3. So meaning our line here is to be at this point. And when our x is equal to 7, our y is equal to 10. So this is to be our x. And this one right here is to be for our y. So our line would now be this one right here. So this is to be our line, which is y is equal to x plus 3. Okay, so I will just be erasing this. So there. And if you are to look at this particular figure right here, if you want to get this area right here at the bottom part, which is this one right here, you can actually solve for it using plane geometry. Since we already have here our base 1, so this is to be 3, this is to be 10, and this one right here to be 7. So for the area of a trapezoid, so for our area, that is to be base 1 plus base 2 divided by 2 times your altitude h. And in this case, our b1 is to be 3. So this one right here is to be 3. Plus, and our b2 here is to be this one right here, which is 10. So 10 divided by 2 times our altitude in this case is to be 7. So 7. So from that, with the aid of our calculator, our area there should be, so 3 plus 10 divided by 2 times 7. So that is to be equal to 45.5. So 45.5 unit squared. So this is to be our area. But in this problem, we are to use integration. So from that, we would be solving for this area right here using the concepts that I have been teaching you a while ago. And let's check if we would be arriving at this particular answer right here. So if you are to use integration, the first thing that we need to do is to introduce a differential area. And that differential area is what we would be integrating. So let's say that this is to be our differential area right here. So this one. So from that, this one is equal to y, and that y is equal to x plus 3. Of course, since this is to be x plus 3. And for our dx, so this is to be our dx. So I think we already have everything we need. So let's just write it in our equation form. So for us to get the area, that is to be the integral of the differential area about the first limit up until the last limit, or the lower limit up until the upper limit. So from that, our x2 is to be this one right here. Since this is to be our x sub 2, that is to be 7, and our x sub 1 is to be this part right here, which is 0. So from that, this is to be the integral of dA. So what is to be our dA? So our dA, or our differential area, is just y times dx. So y times dx. And our limit here is to be 0 up until 7. So there, and I would just be erasing this one right here first for you not to get confused. So it is now equal to, so 0 to 7. And what is y in terms of x, since we cannot solve for this directly? So what is y once again in terms of x? That is to be x plus 3. So x plus 3 times dx. So the next thing that you would be doing is that you would be getting the antiderivative of this function right here. So what is to be the antiderivative of that? So this is also equal to the integral of x dx plus the integral of 3 dx. So 0 to 7, 0 to 7. And from that, using our power formula, that is to be equal to x squared divided by 2, of course with the limits of 0 to 7, plus 3x with limits of 0 to 7. Or we can just rewrite it like this. So x squared over 2 plus 3x, and all of them have limits of 0 to 7. So let's just use this one instead. Okay, and from that, what we would be doing next is that we would be substituting these values right here to this function right here. So for the upper limit, so let's say that our upper limit is to be the yellow part, and our lower limit is to be this one right here. So from that, this is now to be equal to 7 squared over 2 plus 3 times 7. So that is for our upper limit. And for our lower limit, so make sure to subtract it. So minus, so 0 squared over 2 plus 3 times 0. So this is now to be equal to 49 over 2 plus, so 3 times 7, that is to be 21, minus 0, so this would just cancel out. So this is now our answer. And 49 over 2 is basically equal to 24.5 plus 21. Thus giving us an answer of, so 24.5 plus 21, that is to be equal to 45.5 unit squared. So this is to be your answer for this particular problem. And let's check if this answer right here is the same as with our answer a while ago when we have used geometry formula. So it would be this one right here. So 45.5 and 45.5. So confirmed. I want to make a clarification here. We are not indicating plus c in our integration because they would just simply cancel out. So for example, that you would be having a certain let's say x dx, let's say 1 to 2. So this is now to be equal to x squared over 2 plus c with the limits of 1 to 2. So if we are to solve for this already, so this is now to be equal to, so 2 squared over 2 plus c. So that this is for the upper limit. So for the lower limit, so minus 1 squared over 2 plus c. So they would just simply cancel out. So that's why I don't include this value of c in our formulas. So there.